Well, welcome to this seminar. It's my pleasure to introduce today some ideas about surrogate modeling for stochastic simulators. I will explain all the words in a few minutes, but before, thank you very much for the invitation and for organizing also the trip. And Amar forgot to tell you that actually he was a postdoc in my group for like 3 years or so in Zurich. And this community platform, UQ World, that he mentioned, actually, that was his work. So that's our ties. What I will present today, part of it is research that is already a few years old. It's about basically stochastic simulators and how to build surrogate models. And that was mainly developed by 2 PhD students in my group. Back then, now Shujia is a professor in Paris-Saclay University in France, and Nora is still Oberassistentin in my group in Zurich. So I will, well, first of all, explain what we understand as stochastic simulators, as basically simulation techniques that appear in many different disciplines, and why we need surrogate modeling, what it is, and then I will present different techniques that we have developed to build these so-called surrogate models. I will talk about generalized lambda models, that's one technique, stochastic polynomial chaos expansions, and finally spectral stochastic emulators, and then show a number of applications. So what is stochastic simulator? First, I don't know if anybody is familiar with this word. Do you use it, or do you have an idea what it is? No, so that's a good thing. So simulators, probably you know. So I don't know what's your field. My original field is more civil and mechanical engineering, so that's why these pictures here. So typically in those fields we do finite element modeling to represent the behavior of systems, and then when we have a good model, we use these to basically change the parameters and vary them and see what happens under different scenarios. So if we abstract this, basically any of those models, you have a number of parameters that maybe describe the geometry, the material properties, loading, and everything. You run your simulator, which usually solves PDEs, and then you get output quantities. Let's take one. So from this point of view, that type of simulator, standard ones, let's say, if you take an X, you go through this workflow and you get a single Y. Okay, so if you would repeat the calculation with the exact same setting of the model, you get exact same result. Now there are other simulators where basically, if you take the same X, that is really the description of the macroscopic input parameters, and you repeat the simulation, because inside the simulator there are some kind of stochasticity, you get different values. So for the same X, now what you get if you repeat the runs many times is basically different numbers. That is a distribution. So what we want to characterize in that case is a random variable and not just a scalar value. So it's not just science fiction. There are a lot of applications. So for instance, we worked recently in wind turbine simulation and optimization. So here, basically, it's a complex system. You have like a simulation model, which is a high-row servo-elastic with a controller, with fluid interaction and so on. And the input of this is basically what we call the wind box or wind field, which is typically the wind velocity for, let's say, 10 minutes or half an hour. So it's like a big object. But this here is basically generated by a wind generator from a few parameters, which are typically what is the average wind velocity, maybe 15 meters per second for this example here, the turbulence intensity, the variability in space here or in altitude, which is called the shear exponent. So just a few parameters. And here, when you fix these few parameters, in fact, you can generate as many different wind fields, because then you have random processes. So you have Gaussian variables everywhere, and that's power spectral density, whatever. So for just the same value here, you get as many wind fields as needed. And then when you map them onto the structure here as forces, and you compute the resulting produced power or resulting forces in the blades, in the tower, and everything, this is different. Okay, so for a given set of parameters, you now get a distribution of, for instance, bending moments of the blades or produced power. So that's the kind of problem we want to address. This appears also in epidemiology. I don't know if yeah, in this lab, there are people working more in that field, but that was quite popular a few years ago, this so-called SIR model. So basically to model some epidemic, COVID or something else. The simplest model, they consider different types of people. So in that case here, what is called susceptible, infected, and recover. And then basically at each time instant of the simulation, the susceptible people are not yet infected, but can be infected. The infected could recover, and the recover, well, may stay recover, but this could be also some people may die, some people may go to different states of illness, so it can be more complex. But the basic thing is that those simulations here, each of these interactions are also random. I mean, we all know that when we talk about this kind of infections, well, it's not a deterministic process to know if you will get it or not get it. So again, here there are parameters in the problem, but if you start with the same parameters, because of these random interactions that go along the simulation, you don't get the same results. Mathematical finance is another thing here. I will not comment because I have absolutely no clue. That was the work of my PhD student, but basically stochastic differential equations. Somehow, if you look at this term here, the Wiener process term, that's the stochasticity in the model. So if now we define some mathematics for these models, instead of just being a mapping from a set of parameters to, let's say, a vector or output, or let's say just one scalar output here for simplicity in presentation, now a stochastic simulator maps parameters and a probability space to some quantity, which is a random variable, basically. So to understand what it means, if you fix the x, as I said, and you repeat, that is, you change the omega, basically here, you will get different outputs. This is characterized by the conditional response condition on that value of x0. So that's what we will use as a representation for the first methods. And otherwise, if you fix the omega, so this random event, that means practically in the simulation, you would fit what we call the random seed in the random number generators, and you change the x's. Well, basically for each omega 0 or each seed, you will get the standard simulator that is a function of x, basically. So that we call a trajectory. So the third method is based on that description. In practice, as I said, so take the wind turbine example, we have a few well-identified parameters that may also vary. And then we have so-called latent variables that, for instance, allow to discretize random processes, random fields, and so on. Now, when you want to, well, okay, characterize this output, which is, as I said, this conditional distribution for different x's, the basic way would be to do replication. So take an x, do 1000 Monte Carlo simulation to simulate the latent variables, and then you get the distribution for that x. And then you repeat for other x's. The problem is that if you want now to vary also the x's for instance, uncertainty quantification, sensitivity analysis, optimization, and so on, then it becomes completely intractable. So that's why we need so-called surrogate models or emulators or response surface, whatever, meta models, whatever the names. So I hope somebody knows about this. So surrogate models is something clear for most of you. So it's basically replacing a complex code by some models that is learned from limited information, limited runs of the code with advanced statistical techniques, basically, in one sentence. So that's what we want to do here. But so the well-known surrogate models for, let's say, deterministic model, this is, for instance, Gaussian processes, polynomial Gauss expansion, neural networks, low rank tensor representation, these kind of things, support vector machines. And that works. This is well established for models where the outputs are deterministic. Now, if they are stochastic, well, that's an open field. The first idea we had was to represent this response condition on X by a parametric family. But of course, I mean, if it was Gaussian, this is more or less what people call stochastic grading or stochastic Gaussian processes. So if indeed that distribution was Gaussian, it's quite easy to solve, because you basically need just to characterize maybe the mean and the variance of that Gaussian distribution depending on x, and that's it. But in most problems, those conditional distributions are not at all Gaussian. So we try to represent them in a flexible parametric family called lambda distribution, and this looks like this. It's a 4-parameter distribution where it's not the PDF or the CDF, but it's the quantile function that is explicitly given as a function of the parameters, and u is between 0 and 1. So you don't have an explicit representation for the probability density function f here, but you can of course numerically compute it by these simple equations. So those parameters here, they when they vary, they basically can represent many different distributions. So this is an example here. Just by changing those lambda, you can have like almost Gaussian distribution, unimodal, symmetric, non-symmetric, something like exponential. You can have bounded distribution or unbounded depending on the parameters lambda 3 and 4. So it's very wide. So the idea is, okay, if in each x we can represent this by such a distribution, now the problem is to characterize those 4 functions, lambda as a function of x. And if we can do this, then we have a global surrogate model for the thing. So that's what we tried with polynomial Carroll's expansions. I will now explain in detail. So we started with the idea that, well, we need information. So let's start with what we call replications. That is mechanism I explained. For each x, I get not just one value y, but I repeat for the same x different simulations with different seeds, and then I get r different values that would be characterizing this distribution. So, yeah.
Question.
Yeah.
Before, so when, for example, the situation is that you're having, for example, a deterministic case,
yeah,
and you vary the initial conditions, because in many of these simulations you have this Lyapunov instability, and you're getting obviously also then very, very different trajectory.
Mm-hmm.
It would be very simple, similar to the case when you fix the initial seed, even if you're having a stochastic process, then it becomes deterministic. So all of the analysis you're going to show, will this also been the case for that one, that we varied initial condition and then doing a deterministic simulation, then getting distribution of the outcome? Or is it strictly when I'm having a Brownian process like?
I think it's really when you can distinguish between really parameters and so-called latent variables that introduce stochasticity, which is a broad field already. But it does not mean that you cannot turn your problem into something like this. But I don't see now, I mean, not directly how, but I
think on slide 6, if you I think I missed that one there. Or so
no, 6 you said, yeah.
So the last case, when fixing the seed and we're getting the deterministic simulator, does this mean explicitly included or explicitly excluded? In what you're saying, is this the case what you're covering?
I did not get it. If the seed is fixed, then it's deterministic simulator. Yeah.
That means that means the analysis what you're gonna show, yeah?
Yeah.
Will this be also the case when I fix the seed and I have then a deterministic simulator?
No, the idea is that those simulators, for instance, the wind turbine, you need to vary the seed. You cannot just have one. You need many different.
Okay.
So that's the point. I mean, you need more. But we may talk later, because we could consider that the initial condition, if they are the main driver for stochasticity, we could include in those z variable. I mean, in the end, it's always explicit in the computer. You always have to sample some variables. So if you said, okay, this is what introduces the stochasticity, the parameters of the dynamical system, that's x, but the initial condition I put in z, and then I assume this will vary.
Okay.
So I think just reformulating this could probably be meaningful.
Okay, thanks.
Yeah, so basic thing is, or very first step is like, assume we have replication. So we can, for each x, have different things. So again, very basic idea. Let's fit a distribution for each of the x's. So that distribution here corresponding to xi. This will give me 4 parameters, 4 lambda parameters for that point x. Now I do this at many x's, and basically I have now some experimental design that for each x gives me the 4 lambda corresponding to the distribution. So I kind of, because of the parametric shape, I replace the distribution, which is a complex object, by just 4 parameters depending on the x's, and then I just have to fit those things. So first of all, we use maximum likelihood estimation for each point to get this lambda 1, 2, 3, 4 for a particular point, and then with this gathered data, then we can fit any surrogate. In that case, we fit it so-called polynomial chaos expansion. So that's just a link between the lambdas and the x's that are a series of orthogonal polynomials. But we could also take other surrogates here, because now it's we are back to the deterministic surrogate modeling case, basically, with just 4 different parameters, because the distribution has 4 parameters. Lambda 2 has to be positive, so basically we surrogates the log of lambda 2 to ensure that it will be positive. And this we can do typically by polynomial chaos expansions and any kind of solver to get those expansions. But this is 2-step, basically, what I described. Then we realized that it was not so accurate, especially if you have not so many points in the replication. If you have only 10 or 20 points, well, it's difficult to really fit nicely a distribution with 20 points, even if you have now different x's. But you basically split the problem into 2 steps, which is not really optimal. So then we said, okay, let's look at all the data all together. So the x and the corresponding y's, so the joint distribution of this. The distribution of the x's, that's known, that's what we assume. It's typically uniform on the range, or more advanced if we do UQ. And this here is what we want to characterize. So we assume that this is the lambda shape. And then the idea is to optimize now the parameters in this representation of the lambdas so as to minimize the distance, typically Kullback-Leibler distance, between this approximate model and the true model. So we can write down those equations, and this boils down to basically minimizing this expected log likelihood of this complex object here, but where we know basically all terms, when we know the f of y given x is implicit, let's say, with the lambda distribution. And for a given x here, we have here polynomials in x with some unknown coefficients. So in the end, this is a well-posed problem. This is well-posed problem, basically, if we choose explicitly those expansion bases. So if we know exactly the terms we want to put in the expansions, then we have a finite defined set of coefficients A, and then basically we can do this. So to have an idea of what is the nice basis for such expansions, basically we can take the first steps that give an idea of the basis, but not necessarily a good estimation of the coefficients. And then with those bases, we jointly use all the data to fit in one step all the A coefficients, okay? And this here, in practice, this is basically the sum of this log, so log likelihood here at each point we have over all x's and all possible replications. The thing is that when we arrive at this step, in fact, this equation also works for r equal 1. That is when you don't have replication. And this was the next step, where instead of assuming that here in 1D you have different x's, and for x's you repeat the calculation and you have the different y's, in fact we can do something like this. That is, we can take all kinds of different x's, and for each x only a single one, so no replication, just whatever random seed. And intuitively you see that there is more information here than here, okay? It's very graphical, but here basically if you fix the x and then for just a set of x's you do replications in the latent space dimension, you cover less the complexity of the joint space than if you really sample all the x's and all the latent space at once. So this led us to basically have the same representation, but now we can solve problems where we don't need replications, and this way we also expect to need less training points to fit such a model. So basically we choose the x's, and then we just run once the model with whatever a random seed for each x. And then we, of course, then to apply this, we need to know the basis. So when we had replications, the basis we kind of get from the replications. Now, if I want to avoid replications, I have to find a way to smartly select which basis to do. And to do this, we use basically, we based our development on the idea that the lambda 1 and lambda 2, in fact, they, as parameters of the lambda distributions, they have a meaning. Lambda 1 is more or less the mean value of the distribution, and lambda 2 is more or less the variance. So if we are able to find surrogate models for those lambdas as function of x that are consistent with mean and variance, then we can use those bases for the lambda node. That's the way around. If we find nice polynomial expansions for the mean function and the variance function, we can use them for lambda 1 and lambda 2. And then based on many simulations, we realize that for lambda 3 and 4, also they can depend on x, but usually just a small variation with like linear variation in x is sufficient to capture all kinds of variation in the shape. So this is, well, I will not go into the detail, but it's basically how from a set of points like this one here with no replication, how you can alternatively fit the mean function that will be basically something that you will get by polynomial regression, but also the variance, which here on those points is also non-homoscedastic. So you can basically, by this feasible least square method, fit the mean function, compute the residuals from the residual, fit the variance, and then refit the mean function with a weighted least square and back and forth. And basically, with just a few iterations, you get that mean function, that variance function, and this is what you use for the lambdas. Okay, the examples come later. We recently extended this to multi-fidelity surrogate modeling. So generally speaking, what we call multi-fidelity is when you have for the same phenomenon, the same system, basically a so-called high fidelity model that is accurate, that usually is costly to evaluate because it has complex, let's say, physics taken into account, complex mathematical description, maybe very fine discretization for the ODEs or PDEs, and then in the end it's costly. It's also what we consider for physical experiment where basically you have a lot of information, but again, usually little data. And in contrast, low fidelity will be a simplified model, let's say, which is known to have a lower accuracy, but also the cost is low. So now when you vary those x's in this UQ paradigm, basically you can maybe afford 10 runs of the highly costly simulator, but 1,000 of the low-cost simulator. So the idea is to combine this information and get the best out of it. So again, here I will not get into the details of the equations, but the idea is that we can assume for both the two levels of fidelity that they have the same format of lambda, generalized lambda distribution. And as they are linked together because somehow they model the same physics, we basically make a link, or we kind of assume that the distribution of the high fidelity response is basically the distribution of the low fidelity plus some variations for each of the lambdas, where this variation can be very small if the low fidelity is actually accurate. So it's just like a perturbation in a sense of the low fidelity. And so if we put all this together, in the end, we have a similar maximum likelihood, joint likelihood estimation of the parameters of both the low fidelity lambda distribution and the terms that are missing to complement to get the high fidelity. So you will see in results typically here, just with just a few 10 or 50 runs of a costly simulator, providing that we have a low-cost simulator with many more distributions, many more runs, then we can get very accurate results. So that was one thing. So I would say as a summary, it works quite well, but there is still kind of a complex fitting, okay? And there's this lambda distribution, they are very flexible but unimodal. So if your problem, and I know problems where those conditional outputs sometimes are multimodal, that will never work because by construction it cannot be multimodal. So we started to think about how to extend it, and we came to a more general representation. So to introduce it, let's restart here from this GLAM representation. So the conditional distribution has a certain generalized lambda model. So if you use the quantile function, it's basically that quantile function that I've shown at the beginning applied to a uniform random variable gives you basically the CDF of this conditional, or the inverse CDF of this conditional distribution. Okay, so that's another way of seeing the distribution as a deterministic function depending on u, and if u is a uniform variable, what you get by transforming a uniform variable with that function exactly is the random variable you are interested in. And then the idea is, and this is basically how we can, for instance, resample. If you give me a new x and you ask me, okay, but how do I get samples from this conditional distribution for a new x? Basically, that's what I would do. I would basically sample uniform numbers and put them into the previous equations with the proper lambda for that x, and then that gives me samples from that distribution. But once we have we agree on this, actually here, this is just a particular mapping from, so we call this iso-probabilistic transform in engineering, but there are other names, basically probability transform from a uniform to whatever given distribution. There is no reason just to have this 4-parameter format with a particular function. So we can imagine here, do the same, that is, consider that the conditional random variable is equal in distribution to a mapping of a certain latent variable z. Of course, this mapping depends on each x. And then we'll try to identify this in a more general family of functions. And that's where we, again, use so-called polynomial chaos expansion. So the final formulation is given here, and all details are in this paper. So polynomial chaos expansion, is it clear? It's just a polynomial response surface. Let's make it this way. So usually, if you have a deterministic model, you replace the output, or you approximate the output by a sum of coefficients times polynomials in X. What we do here is that we add an additional artificial latent variable, and this basically with a single variable, it intends to capture all those latent variables that you add in, let's say, random process discretization and everything. Here we just need one to acknowledge this stochasticity. And if we just use it, it's actually ill-posed, so we need some terms to regularize the thing here. So that's the final thing. So here what is unknown is, okay, we have to decide for the basis, how many terms in these polynomial expansions do we have. But once this is found somehow, we have to compute the coefficients, C alpha, and we have to compute the variance of this noise variable that overall gives the best fitting to the distribution. So here it's just, again, a graphical representation to show that for standard symmetric or non-symmetric distributions, but also for unimodal, if you have data from those distributions, then you can fit such an expansion quite well. And if you put more points, this converges to what you want. So this should work. Okay, so now remember the GLAM distribution, I had the quantile function explicitly. So after a transform, I can also more or less have semi-implicitly the PDF, the conditional PDF. What is the conditional PDF of y given x from this construction here? Well, you can see it here. Here, that noise term is a Gaussian variable. And basically, if you fix the x and the z, basically here you have just the distribution of a Gaussian variable. And now z has a certain distribution of your choice. Again, we typically use uniform. So you can basically make a convolution and solve the problem for just y given x. And that looks like this. So at this stage, still, we have not identified the parameters. So you can think about it as a very generic so parametric, but with many, many parameters distributions. And the parameters are those C alpha coefficients in a sense. And this is in the end not explicit, but there is just a 1D integral here, which is something that we can do easily. Before I show you how we can compute those coefficients, the nice thing with polynomial chaos expansion, so again here, if you know, you will recognize. If you don't know, I will try just to give you the best of it. If for a second you forget the z and the epsilon, so the standard C alpha, psi alpha of x, the standard expansion for deterministic surrogates, this is quite popular and quite powerful because we choose here orthogonal polynomials, meaning that then the moments and many statistical characteristics of the response are contained in the coefficients. Namely, the C0 coefficient is in fact the mean value of that function here as a function of x. The variance is the sum of the square of the coefficients, and then we can also derive sensitivity indices. So here, that's the same because it's the same format, just extended now with one additional latent or artificial latent parameter. So for instance, given my cloud of points, the mean function, the mean response as a function of x, it's an explicit polynomial that I extract just from this representation. The variance function is again an explicit polynomial with those coefficients and those functions. And if you are into sensitivity analysis, where standard technique is to compute the so-called Sobol indices for sensitivity analysis, again, everything here is explicit based on the coefficients, of course, once you have computed them. So this means that we basically keep all the nice feature of the standard polynomial chaos expansions also in this setup and with some additional information. Okay, now we have to fit it. So again, well, it's quite technical. So if you're really interested, I suggest you either read the paper or use our software toolbox that implements this thing. But basically, this is the conditional PDF. So now for a particular x and corresponding y, basically if I replace by x and y here, that will be the likelihood of this observation of this data point. And this is a function of the C coefficients that are unknown and that sigma epsilon here. If we disregard sigma epsilon, suppose we know for now, then we can basically evaluate the integral, these outer integrals by typically Gaussian quadratures. So in the end, we get quite cheaply here the expression of for each point of the likelihood or log likelihood as a function of the coefficients, and then basically we just have to maximize this as usual using all the data points, all the n data points. But in practice, so the sigma epsilon is the variance of this residual term, let's say the variance of the regularization in a sense. But that, of course, we don't know. So how to get it on top of it? Now we need cross-validation. So we basically test different sigma epsilon. And to test it, basically, that's standard cross-validation. Instead of using all data at once, we do different folds, let's say 10, and we would fit the model with 9 folds out of 10, and then compute on the remaining fold of points, or 1/10 of the points, we will compute, the performance of the model, that is this likelihood, once we have basically solved the problem. So now we have substituted the solve coefficient. And so this here, in the end, is a kind of measure of how good the model is given sigma. So then we can basically optimize in just 1D what is the best sigma to use. So yeah, I mean, it's a number of steps, but in the end, it uses classical tools from statistical inference. Still, there is the question of that. Here, how many terms? So this is basically the set of polynomials you keep in this truncated expansion. So how many terms would you take? So again, back to standard sparse polynomial chaos expansion for standard surrogate models. This is very mature. There are algorithms that basically find automatically the sparse basis that is the best explaining your data. There are even benchmarks and surveys about nowadays the best techniques to do so. So here we can basically also adapt all those to the case of stochastic polynomial chaos expansion. How much time do I have in total? 1 hour. Okay, so then I can try to present the third, or at least the ideas of the third approach, because it's quite different, and then I keep time for examples. So the third approach is much more close to representing basically random processes, or consider the stochastic simulator as a random process. So again, if I repeat my introduction, for a given x, we have basically many different m of x depending on the random seed. So we have a distribution, okay, conditional distributions. That's what I have modeled so far with 2 methods basically. But we could look at this. That is, we fix the random seed once, and then we vary the x's, and then we get, well, now a deterministic function for omega 1 and another function for omega 2 and so on. So this is basically just a standard function. So if I put all the two together, basically a stochastic simulator is nothing but a random field process, depending on your preferred wording. So it means it's a collection of random variables indexed by the x's with a very complex non-Gaussian, non-stationary joint distribution. And the idea is, can we somehow characterize this complex object, now considered as a random process, but not in 1 or 2 or 3 dimensions, but in as many dimensions as x parameters, so it can be 10. Can we represent this with the tools of random processes, basically? So typical representation for random fields are so-called expansion methods. So the idea is to replace this random function or random field as sums of deterministic functions multiplied by random variables, so kind of splitting the variables between what is the x's and what is the stochasticity. So this b function here would be representing the spatial variability, spatial space here meaning the space of input parameters. All this wording comes from like 1D or 2D spatial variability, but here we do this in the higher dimension space of the x's, which can be much more than 2 or 3. And this AK would be random variable. So basically the idea is that the trajectories I've shown before here, x is just 1 dimension. It's like I want to basically represent them on certain basis functions and then have some coefficients for this. And the workhorse method to represent random fields, probably you know if you're familiar with some stochastic methods, is this so-called Karonen-Loew expansion. So this is like a very old result. If you have a random field characterized, let's say 0 mean and unit variance, very simple, but characterized by a certain covariance function, you can expand this here as an infinite sum, as a series of functions of space multiplied by variables and some eigenvalues. And those terms here, the lambda and the phi, they are basically solution of an eigenvalue problem. So it's basically a continuous version of principal component analysis, if you want, or if you're not familiar. But that's the continuous version of it. And so you also have a kind of continuous eigenvalue problem, which is here an integral eigenvalue problem. But in practice, when you can't have the analytical solution, you basically discretize things, and in the end, it's principal component analysis. So the nice thing is with this representation is that the phi are orthogonal. These are eigenfunctions, so basically they are orthogonal to each other. And the lambda are also orthogonal in the random space, which means they are 0 mean and unit variance, and they are uncorrelated. But they are not independent, okay? So those psi here are 0 mean, something's missing, 0 mean unit variance, and oh no, everything is there, and uncorrelated. If in the most of the applications you have this expansion and you start from a Gaussian field, then it's extremely easy, because if there are, if this is a Gaussian field, then the psi are Gaussian, And if they are Gaussian uncorrelated, well, then they are independent. That's equivalent for Gaussian. But generally, you can have a family of variables that are uncorrelated, zero linear correlation, but they are dependent. They are a complex joint distribution. So here we are in the complex case in general. And now we use actually a bit more, very similar, but just one step more. In fact, the x's in our case, now they are not just like pointing the space coordinates and just like indices for space. They are actually parameters that then we also consider as being random in the context of uncertainty quantification. So they are not just like a range, they also have their own distribution. So everything here actually has been extended by mathematicians like some 20 years ago, where if you have here some weighting function, which would be a PDF, everything is just the same. So you have exactly the same results. It's just you acknowledge also that the x's here have a certain underlying distribution because you are in a context where they also are. Okay, nice. That's the theory. Now, what can we do out of this? What we have, remember, was a set of data points, this cloud of points. So here we add the constraint that still we have trajectories, meaning that what we will simulate is not points everywhere, like for each x, whatever random seed, but basically we take a random seed and from that random seed, we take several x's so as to have at least a number of points of the same color. So it's not anymore vertical, it's horizontal in a sense. Not necessarily with the same axis for the different curves, but not the same number as well, but at least points on curves that each of them corresponds to a particular random seed. First step is, that's how the points look like, and we assume that there are underlying trajectories if we have many points, which are those lines. But what we have in practice is just this cloud of points. So what we will do, remember each line or each color here, now it's a deterministic function of x, so we can do a surrogate as usual. Gaussian processes, polynomial chaos, whatever. So here we use polynomial chaos because it fits well with the rest. So we will start by taking those R different trajectories and with the data, so the points of each color, basically feed a surrogate that is more or less what you see here. Each of them has a set of coefficients, so assume that we put them in the same joint basis with the same psi alpha. Each trajectory now, so you replace the points by really something continuous, which is a polynomial, and which is characterized, each of them, by just a set of coefficients. And with this representation, now we can basically consider that we have different trajectories of a random process that are now being made continuous in a sense because we it's not interpolation, but we basically surrogated it. So we can use these trajectories to analyze the random field. That is, based on this trajectory, we can compute an empirical covariance matrix of the field, decompose it, and then from this decomposition get the eigenmodes here and the eigenvalues. And then once we have those eigenmodes, if we kind of reproject those trajectories, we will get basically also the realizations for our data points of this missing psi variable. So in practice, there's a lot of nice mathematics, again, described in the paper that must be cited somewhere, but starting from those PC trajectories, so remember we have basically for each trajectory, let's say capital P coefficients, and we have R different trajectories with this matrix of coefficients C, basically, analyzing the covariance function or decomposing the covariance function computed from this data is equivalent in the end to do principal component analysis of those coefficients. That is basically solving an eigenvalue problem of this CC transpose matrix. Okay, and if you do this, basically the eigenmodes of these eigenvalue problems are basically the phi variables, the phi functions that I have defined before, and you define them with the eigenvectors of this problem here are basically the coefficients of the psi polynomials for each of the eigenfunctions. So yeah, it's basically somehow doing some discrete Carinian Loewe expansion or principal component analysis in two different dimensions, and in the end, it's basically equivalent. Okay, so there is a third step. Now we basically, in this equation, in this representation, we know everything but those realizations. So basically, we restart from the data points to get now realization of those random variables. And then, as I said, if this here was a Gaussian, that is, if my stochastic simulator for every x had a Gaussian distribution, we're just done, because the psi must be standard normal Gaussian variables, full stop. But in practice, it's not. You remember, or no, you don't know because you have not seen the examples yet, but you will see in most cases, these conditional distributions are not Gaussian. So this means that when we kind of normalize the data to these 0, 1 psi variables, we have a complex joint distribution, which is absolutely non-Gaussian. So to do this, well, we have tools to do this. So it's another thing where we basically use previous research, but it's kind of independent. If you have complex, the data set with complex dependencies between the variables, the usual way to represent it is to decompose into univariate marginal distributions and a copula function that captures the dependence. Here we have more information because we know that for each of these psi separately, each marginal must be zero mean and unit variance because they come from this eigen decomposition of this Karonen law decomposition. So we can basically do usual inference for the marginal, but adding some constraints because we know that they should fulfill it. And then, yeah, we can typically do some parametric inference and select between different models and then compute the copula. So this again, and nothing very new here, but we use our software for doing this inference, but any software that would do multivariate inference would work. And in the end, that's how we get this so-called spectral stochastic emulator. So again, it's a surrogate model of the original thing. If you give me new x's, I will simply resample the psi variables and recombine this, and I will get samples of that conditional distribution. But if you give me a seed and you want to know the trajectory for that specific seed, basically, you just fix the psi, and then you will get a representation of the trajectory. So it works in both dimensions. Yeah, 10 minutes for applications. I think that should be okay, and lighter also. So does all this work, and is it useful? Well, before showing the applications, I need to explain how to validate if this works or not. Because, again, if you know surrogate models or whatever machine learning models, how do you validate that it works? Basically, you have some training data. Usually, you keep separate some validation data, and then once you have trained your surrogate, you apply it to your validation data, and you compute a mean square error between what your surrogate predicts and the real values. Because it's scalar. If it's a vector, okay, it's mean square between vectors, but that's okay. Here, we want to validate if a predicted distribution given x is close or not close to the real distribution given x. So we have to compare distributions. So we tried many things to compare distributions. There are all kinds of metrics to do this, from Kullback-Leibler to different Wasserstein distance, different, Kramer von Mises, whatever. What works the best is basically computing distances between quantile functions, because this is basically the most well-posed. So basically, we will, if we have some reference distribution and some predicted by the surrogate, we will compute this so-called 2 Wasserstein distance, which is the mean square error between the quantiles in the end, from the true one and the surrogate one. And this is for a given x. And now we have, of course, we want a model to be accurate for different x's in our input space. So we basically typically average this over x. And after normalization, then we get a number between 0 and 1. Well, usually between 0 and 1, but typically in terms like at 10 to the minus 1, 10 to the minus 2, which is the global accuracy of this stochastic surrogate. First example, the wind turbine. So I described at the beginning. I will not explain it again. Now we have real data for a real model of a wind turbine and realistic wind scenarios. So we have here, that was the beginning of our work. So we still add replications for the training points. Now it's not anymore needed, but at that time we had like about 500 points with replications. And then to validate, we have less points, but many more replications, because for all these points, we want to be able to kind of plot the real conditional distribution. So 500 points is basically needed. And so here now, once everything is fitted, we get here like a 1% error, which is in that case actually very good. And what you see here is for different x's. So x here in that case, those few parameters. The first one is the mean velocity of the wind field that is used. So like 8 meters per second or 11 here. Second one is turbulence intensity. And the third one is some shape factor, basically. So the histogram would be basically for that value of the three parameters, we take the 500 values that we got from real 500 wind turbine simulation and plot an histogram. And the blue curve is what we can predict based out of the surrogate. So typically works quite well. And then if you look at other quantities, scalar quantities, not just the distribution, because we also like numbers. If we compare on those 120 validation points, the mean value of the distribution, the variance or certain quantiles from the surrogate or from this real validation set, we get this kind of accuracy. So typically, yeah, 98%. Here in that case, 83%. But yeah, around 90 to 95, 98% accuracy on those scalar quantities, be it mean value, variance, or quantiles, which is quite good. Just as a remark, so this extensive simulation in the engineering practice nowadays, the engineers who design new wind turbines, they know, of course, that there is the problem of stochasticity, but the standards and what engineers do, they will use 6 replications, sometimes 12, and they take the worst case of the 12, and that's the way they handle the stochasticity. So you see that, well, we can make some progress with these kind of methods. The stochastic epidemiology model. So again, we start with a given population. At the beginning, we have 3 types of parameters. Well, basically, we have some susceptible, just a few infected. Again, we don't know exactly, so we want to take this uncertainty into account. And then the system dynamics, so how this epidemics spread is governed here by mainly 2 parameters that again are not well known in practice, so you have some uncertainty. And so what we predict is, okay, we let it go, and then we want to know how many people were infected during the outbreak. So not counting the number at the beginning, but the new people infected. And again, if you fix those few parameters here, you run different simulations because of the internal stochasticity of the contacts. Basically, you get different numbers. So again, you get in the end distribution condition on those 4 parameters. The first one being the initial population of S, and the second being the initial population of I. Again, here, well, quite good fitting. Also, much better than a typical pure non-parametric, so kernel-based density estimation, which when you have a lot of data and small dimension is a technique that could work. You see that here it really is not really competing. We can also design, look at convergence, make sure that if we have more data, we get better results. That's the least to obtain. And you see that we have at least here in terms of this average Wasserstein metrics, we have at least 1 to 1.5 order of magnitude more accuracy than the usual kernel-based method. And in that example, the GLAM or stochastic PC are basically equivalent. Because the distributions you see, they are like very nice. They are not far away from Gaussian and certainly unimodal, so everything works well. Finally, just an example of multi-fidelity. So that's recent work. So here, the object of interest is a building, model of a building. So we are back to civil engineering. And we shape this building with an earthquake here at the bottom, okay? But shaking with a single earthquake, you don't learn much because you cannot predict how the earthquake will be big. The only thing you know is from recorded earthquakes, you can do statistics, and then you can do models or synthetic earthquakes that are relevant to a certain zone of seismicity. So this synthetic ground motion, exactly as the wind field for wind turbines, you can generate them basically with a few macroscopic parameters and then tons of Gaussian variables that basically will give you, should have put this like these nice signals of earthquakes. So here we have 4 parameters that basically contains the physical properties. So IA here is called Arias intensity. That's more or less the total energy of a given earthquake over, let's say, a minute. T mid here is basically the time where you have the peak oscillations. D something here is basically the duration, let's say, and omega is the main frequency. Of course, it's non-stationary and complex, but let's say the main frequency. So these are physical parameters that make sense, but out of them, you can generate millions of different earthquakes. So we do this here to basically get typically the distribution of the maximal horizontal displacement, because those buildings collapse when the inter-story displacement is big. And that's the problem for risk analysis. And in our case here, we had 2 solvers. The high fidelity is what people would do. It's not too demanding here because it's a very simple building. But if you imagine same analysis for a tower of 60 floors and beams and floors everywhere, of course, it will not be 10 seconds, it would be hours. And then the low fidelity is basically degrading the solver. Again, same Wasserstein distance. And here the point is to show that there is, again, to basically not just take this quite advanced and accurate high fidelity model with many points, but just take few of them or less of them, and in parallel take these low fidelity values, which just by themselves will not be very good, but combined with the let's say 100 or 200 high fidelity points here, will give you something better. So you see, the red thing is what you can get with just 100 or 200 or 400 points. So it converges, but slowly. But if you just take the minimum value here of 100, but combine with something that is very inexpensive, suddenly you get much better accuracy. Of course, if at some point you have a lot of high fidelity points, then the multi-fidelity framework does not bring anything anymore, because just the high fidelity contains a lot of information, is accurate, so you use it. Well, these are, again, comparison of distributions. I think it's time for conclusion. Exactly 1 hour. So stochastic simulator, at least I gave you 3 different examples, so I'll give you a flavor of what it could be. I'm sure in your own fields there could be applications, maybe in non-linear dynamics and chaotic systems. Why not? I have not tried. The idea of the surrogate models, why it's difficult is because what we want to emulate is not numbers or vectors, is really conditional distributions, which make it more difficult. So you can find a few papers on this already. Now other groups in the world start working with these techniques and further develop it, which is nice. We also put all our developments in our in-house software called UQLab. Again, Damar was a big contributor of this software during his time in Zurich. He basically developed the high performance computing module that we still use a lot. So that was a big task. And so if you're interested in uncertainty quantification in general, just have a look at our website, uqlab.com. It's in MATLAB, but there is a Python version. And now it's there for 12 years or so. We have close to 10,000 users worldwide. So it's, let's say, a quite mature toolbox for UQ. And this is Damar's work, UQ World. That has not changed. So this has been enriched by many contributions of many people, but you see the layout is your layout. And with this, I thank you very much for your attention.
The forum for questions. Check your online.
Yes.
Exactly. So you're estimating the conditional distribution of y. And you said in the beginning that you don't use Gaussian processes because you assume a Gaussian. But here you have a Gaussian again, and I got a bit confused here. Could you please elaborate on that?
Yes. So Z here is, let's say, auxiliary variable. So let's say it's Gaussian, but it's uniform. Let's say it's uniform. So with just this polynomial of this variable here with different coefficients could represent any distribution basically, because if you take uniform and you have the CDF of the variable of interest, basically the CDF of this variable is or f of u is the CDF of that variable, and this f CDF function, I mean, it's integrable, square integrable, so you can exactly represent with a series expansion of this kind. So okay, then there is approximation with truncation, but you can represent. And so here you can represent absolutely any form. So x being fixed, this is a polynomial in, let's say, a uniform variable, and it can take any form, so you can mimic any type of distribution. So we would be happy with just this, but then for reasons that you can read in the paper, if you just take this, you can get basically, there are many cases where you would get infinite values for the likelihood when you try to estimate the coefficient. So it's ill-posed. Basically, because you probably know when you transform the PDF, the density of a variable with a certain function, if you have zeros and singularities, you get singularities. So to avoid this, we need some regularization, but otherwise, it's a general purpose representation of random variables. Yeah.
I see. Okay, thank you.
So it can be reused also in a completely different context. Maybe that's the question. Yeah. Michael.
Yeah, many thanks for the nice talk. Of course, ask a question. So in the examples you showed, we had a 5-dimensional or four-dimensional, then a 3-dimensional, and I don't know, the last one. So this is the typical size you can address computationally?
At that stage, yes, that's the point. That was really the first, let's say, set of PhD and work on this. So we started from no method and apart like pure non-parametric things. So indeed, at the end of this work, I think the largest example is probably dimension 8 or 10. So it does not address high dimensions yet. But the answer is also, if you take standard modeling with many input parameters, probably if you have experience with sensitivity analysis, you know that you may have 50 parameters in your problem, but maybe just 5 of them play really a role, and the rest you need, but in fact, they play little role. Even if they were varied, that does not change much the response. So if now you have many parameters, some of the x's you put in the z, and then you're back to, so you need probably some prior, let's say, simple sensitivity analysis to really focus on a small number up to 10 x's. If you have many more than that, then you should reduce somehow, which probably does not cover all possibilities, all problems, but still many problems with many parameters. If you look carefully, you just have a handful that is really important. So that's how I would handle this.
And another question, I mean, the psi alpha, these are usually some orthogonal polynomials like Chebyshev
Chebyshev.
And the coefficients you then estimate by some kind of quadratures or something.
No, that's the point. So in the standard way, so in the history of polynomial chaos expansions, well, in the history, first of all, that was what people call stochastic Galerkin method. So it was intrusive with the PDs, basically. Then some 20 years ago, people moved to something non-intrusive with the idea that if you have a solver and you want to make stochastic the parameters, you don't want to rewrite your solver. So that brought to some quadrature methods and projection and quadrature. And then in parallel, there are, let's say, methods more in the idea of just solving least square problems, which are emerged in parallel. And the latest version of this is what we call sparse polynomial expansions, where basically, which is more based on, well, least square and compressive sensing, or penalized least square, where basically you have your data, you don't assume any polynomial truncation.
With the pre-choosing of the basis.
And so that's why now, for a classical case, you have nothing to do. You put your data, press the button, like in UQ you have all kinds of options. But if you're not familiar, you really put your data as you would do in scikit-learns for, I don't know, Gaussian process, whatever. You have default options. Put your data, press the button, you get a good surrogate, if the data allows to do it. Now here, the problem is that the inference in that context, because we represent now conditional distributions, the inference is going through some kind of maximum likelihood. So the process is more difficult, and it's clear given the basis. So that's why we need some information to find the basis. So we also have this sparse basis, but it's not as direct. So there is a lot hidden here where you.
And then it's given the sparse basis, then it's a kind of a Lasso regression.
Yeah.
Okay. That answers the question perfectly. Thanks.
Okay. So it's not projection and not quadrature. Yeah.
Okay.
Not sparse quadrature also.
Let's
There is another one in the room.
If you go from the low fidelity to the higher fidelity models, how large is the overlap? Is it simply that you extend the lower fidelity models, or
you mean the models that generate? It can be anything. So it can be. We had also, I think she has examples in her PhD. Some structural, so civil engineering structural problem with beams and stuff like that. What we call high fidelity would be like a description with a finite element model. And the low fidelity, it was just an analytical function that basically you just take the equivalent beam of some system, and for that equivalent beam, then you have analytical expressions for what you want to compute. So it can be anything. In my example here, it was kind of the same modeling with, let's say, a very accurate solver in the time discretization versus inaccurate solver. So it's a bit artificial, but it could be a finite element model with a coarse mesh versus a very refined mesh. It could be, if you do CFD, a model that I don't know, takes for fluid runs model versus something more simple or more complex. So different physics, different meshing, different whatever. Provided the only constraint, I think, I'm not even sure now, I don't remember, but probably it's easier if those models have the same parameters, or at least the input parameters of the low fidelity is a subset of the input parameters of the high fidelity, so that you can put those series easily. But otherwise, there are ways to manage. So.
Well, I do have one question. In the next slide, you mentioned about stable indices.
Yeah.
And try to make sense of it. So the denominator is a total variance that uncertain controllable inputs and intrinsics. So is there a possibility where you all sum up all the possible interaction from the controllable inputs? The indices
you can basically
like much less than one, and then
yes. In fact, so if you don't consider the epsilon, suppose it's very small, like the variance is very small. If you fit a good model, it's anyway very small. So here, what you get is really a standard polynomial chaos that depends on the input and on a single auxiliary variable that captures all the stochasticity. So then you can say, okay, what is the importance of the stochasticity versus the variability of the inputs? What is the interaction of them? Is there higher order terms? All this you can really compute. And in that paper here, Shuja basically also, you can have different kinds of Sobol indices based on this stochasticity. So what I explained now is one way, but you could say, okay, I want just Sobol indices of the mean function. So then I reduce the stochasticity to the mean function, and then now it's a deterministic function, and I do importance of the input parameters on that mean function, or on quantiles, or so you don't just have one single definition. You could do different things, but for sure you can characterize the importance of stochasticity versus variability of the rest. That is clear. So controllable versus uncontrollable, if you want.
As a follow-up, so if the intrinsic stochasticity dominates, what's the implication to engineering design?
Well, it's not necessarily a problem if you take this into account. It means that simply, well, you cannot take the mean value of the distribution for design. So again, for the wind turbine, what they do, so in a lot of assessments, they would take just a few replications and the worst case, so the highest forces or highest whatever. And if it's okay, they say it's okay. Well, I guess if I do more simulation, I may end up above. Sometimes they do a bit more than that. They have not necessarily much more points, but they would try to fit a viable distribution. But if you do this on 20 points, you see, can also be very uncertain. And then take quantile. So again, not the mean value, but quantile. So it's in practice, at least for a wind turbine, where it's really part of the industrial practice, they cope somehow with the stochasticity, but certainly not in a very, let's say, coherent or very well posed way. So we hope that what we did here, and that has been applied to different problems, will basically migrate to also the applications.
Questions before we close today's seminar? And thank you again.
Thank you very much for